My lab report for physics lab 4. So as an introduction to this lab, the purpose was to create and examine a variety of series and parallel RC circuits. I also used the principles of charge conservation and the loop rules to explain the multimeter measurements I took, and then compared these measurements to predicted values. And I found that the time to charge or discharge the capacitor was about 30 seconds, and the multimeter measurements support the node and loop rules. So an introduction, some key physics behind this. We have Kirchhoff's loop and node rule, and these are the equations for those. The loop rule demonstrates the conservation of energy, where the sum of the voltages throughout this series are equal to 0. And then the node demonstrates conservation of charge, where the current in of a node equals the current out. And then the steady state circuits, constant flow of current, is the key assumption to this lab. The calculations wouldn't be possible without it. And then we also have Ohm's law, where the voltage across a point is equal to the current times the resistance in RC circuits. So for the experiment, basically built two circuits, one where there were two resistors in series, and I took ammeter and voltmeter measurements at different points, and then also an RC circuit with a light bulb and capacitor. And the system in this case was the batteries, wires, bulbs, resistors, everything in the circuit, and the surroundings was the rest of the environment, which pretty much didn't have an effect on the measurements taken. So this is circuit 1, two resistors in series. You can see these 4 pictures. I'm measuring the voltage and the current across each resistor in each of these 4 pictures. And in the circuit we have two 1.5 volt batteries, and I found the voltage across the 100 ohm resistor was 2.7 and 47 ohm was 1.2 volts. And then across each resistor for 100 ohms it was 51.3 milliamps, and 47 it was negative 28.8 milliamps. And this demonstrates and supports the conservation of charge, which you can see in the calculations in this slide. So the assumption is that the sum of potentials is 0. So I calculated the potential values using the resistance and current measurements, and I found 100 ohms times 51.3 milliamps is 5.13 volts, and for 47 times this current, the negative 28.8, it's negative 1.35 volts. So summing these, get 3.78 volts, which is approximately the sum of the measured voltages, which is 3.9 volts. However, there's a small error because the voltage does not add up to 3 volts like it should for two 1.5 volt batteries, which could just be due to errors in the instrument. So this is a potential graph of circuit 1 where it goes up for the batteries to the supposed 3 volts and then goes down as it crosses each resistor to 0. This is circuit 2, the RC circuit. There's a 9 volt battery, capacitor, and did it with 2 different light bulbs, a 10 ohm and then a 20 ohm light bulb. And the observations were as the capacitor charged, the light bulb dimmed. It starts really bright and then it dims. And then yeah, when you unplug the battery, the capacitor slowly discharges, and this makes the light bulb get brighter, and then it goes out. So it took about 30 seconds for the 10 ohm and then 1 minute for the 20 ohm. So for the discussion, what if you did this lab with a virtual circuit instead of a real life one? Well, a real emitter has internal resistance leading to a small decrease in current. So if you did it with the virtual circuit, which I tried out, the measurements are more ideal and more line up with the theory and the equations behind it. And then similarly, if you did this lab with a real battery and capacitor for the RC circuit, or if you did it on the simulation instead of with a real one, the measure time to charge the capacitor would be different because it's just harder to measure the actual charge of the capacitor than it is to predict it with a model, and there's more factors at hand. Thank you.